All right, so we've been talking about logarithms. Now let's actually use them to solve some equations. All right, so the key thing that we need to first observe is that exponentials and logarithms both are one-to-one functions. So what that means is if we have the same base, and if these two things are equal, then we know the exponents are equal, like s and t would be equal in this case. All right, so how could we use this? If we had this equation, 2 to the x minus 1 equals 2 to the 2x minus 4, we know if these are equal, they have the same base, we know the exponents have to be equal. So then we just have a linear equation to solve, right? X minus 1 equals 2x minus 4. We just, solve that for x. So this is a key observation. We're going to use it again for logarithms later, right? If these are equal, then we know the exponents have to be equal. All right, so one strategy that we're going to use for exponential equations is rewriting them so that these have a common base. Okay, so in this example, the previous example, these both had base 2. So it was easy. We could just set the exponents equal to each other. In this example, they don't have base 2, but could we rewrite them so that they had the same base, namely 2? Yes, we could, right? We could say, well, 8 is 2 cubed and 16 is 2 to the 4th. And then we just could rewrite the exponents, 3x plus 6, 4x plus 4, right? And then we'll have these two exponents equal to each other. So 3x plus 6 equals 4x plus 4 equal to 2. All right, so it's similar to the last problem, except we had to do a little work to make these bases equal to each other. All right, how about here? 2 to the 5x equals square root of 2. This is disguised to be square root of 2, but really we could think of that as 2 to the 1/2, right? And there we are. We've got two equations. We have an equation where the bases are the same. We can set the exponents equal to each other and solve for x. How about this? 3 to the x plus 1 equals negative 2. Can we rewrite this in any way so that they have the same base? No. And let's just think about this for a minute. 3 to some power equals negative 2. Is there anything that could make that true? 3 to any power? No. This has no solution. Okay. There's no value of x, no real value, that's going to make this a true statement, because this to any power is going to be a positive number, right? Even if this exponent became negative, it's still going to, it could be like 1/3 or 1/9 or something like that, right? But there's no way that this is going to become a negative number. So there is no solution to this exponential equation. Okay, here's the second strategy. So the first strategy we just talked about was writing both bases to be the same. Second strategy is this. Let's see. 5 to the x plus 2, 4 to the x. Different bases. Can't really write these as powers of the same base. So here is a big trick. You're going to use this. This is actually very clever. It is very useful, and you will use this in calculus if you take calculus as well. You take the natural log of both sides. Okay, so here's our original equation. Take the natural log of both sides. Why is this helpful? Well, we have that power rule. We can pop this exponent out front. So natural log of 5 and natural log of 4, they're just numbers, right? So this actually is looking pretty good for solving for x, right? We can distribute the natural log of 5. We can bring all the x's to one side of the equation and all the numbers to the other. And now we're going to factor an x out of both of these terms. And we can divide by this. First they combine them. Natural log of 5 minus natural log of 4, we could write as natural log of 5/4. So they rewrite this using properties of logarithms, right? They say this is an exponent of negative 2 to get natural log of 1/25. You're just looking for a number here, right? So you can combine this, not combine it. At any rate, then you divide by natural log of 5 minus 4. At this point, you could have divided by this, right? Just to get x equals negative 2 natural log of 5 divided by this. I don't know if this is any more compact. But this is a number, right? If we wanted to, we could just put this in our calculator to figure it out. Or if we wanted it in an exact form, we could leave it like this. The key step here is take the natural log of both sides and then use that to bring the exponents out front. Okay. All right. What if you have something, you already have e here in the equation? So what can we do? Well, let's look at the solution. We can divide both sides by 20, right? So that just leaves us 5 equals e to the 2t. And now we could take natural log of both sides, right? So just like last time, we can take the natural log of both sides. This is just a number. Natural log of e to the 2t is just 2t, right? Divide by 2, there we go. So taking the natural log of both sides of an equation is very clever. It's very useful when your variable is in the exponent because of the properties, the power rule of logarithms, right? You can bring that out of the exponent, and then we have a lot of tools to use. All right, what if we have this equation? Can we simplify this at all? Or what I'm seeing here is this e to the 2x, right? If we could isolate that e to the 2x, I think that would be a good first thing to do. So let's do that. Let's bring the 5 over, subtract 5, divide by 4. Now we have e to the 2x equals 7/4. That looks like before, right? We can take the exponent has the variable. We could take the natural log of both sides. And there we go. Now we just have 2x equals this number, natural log of 7/4. Divide by 2 or multiply by 1/2. And we're left with x. All right, here we're going to get something called an extraneous solution. E to the 2x minus e to the x equals 56. This is kind of a tricky problem. Let's look at the solution. The first thing they did was bring 56 over here. And then they said, aha, this is like a quadratic, kind of, right? We could factor this like a quadratic. That is a clever thing to notice, okay? We could factor this like a quadratic to get e to the x plus 7, e to the x minus 8. So think about that a little bit. If we multiplied this out, we get e to the 2x minus 8, e to the x plus 7, minus 56, right? So we can actually factor this as if it were a quadratic. And then we use the zero product property. So we set this equal to 0 and this equal to 0, just like we do with quadratics. We solve for e to the x, we solve for e to the x. And what happens here? E to what? This looks kind of like the problem we had before where there was no solution. Is e to what power is going to give you negative x? Nothing. Because think about the graph of e to the x, right? An exponential graph. The range is from 0 to infinity. There's nothing that's going to make this equal to negative 7. So this gives us no solutions, but this does give us a solution. E to the x equals 8, and then we can take the natural log of both sides. We get x equals natural log of 8. Okay. We can also just use the definition of logarithms. So here, instead of having e to some power in our equation, here we have natural log. So strategy is going to be the same. We want to isolate the natural log. So subtract 3, divide by 2. So bring 3 over, divide by 2. We get natural log of x equals 2. Now we can just read, what is this saying? This is saying e squared equals x, right? The definition of exponential or logs. E squared equals x. So e squared is just a number, right? We could put that in our calculator or leave it in exact form like that. How about this? 2 natural log of 6x equals 7. Again, let's isolate the log. So we divide by 2. And then right here, we can write this as e to the 7/2 equals 6x, right? Using the definition of logarithms. Write this in exponential form. E to the 7/2 equals 6x. And I don't want to move my mouse so that thing doesn't pop up, so that you can see now we just divide by 6 or multiply both sides by 1/6. And that's a number. 1/6 times e to the 7/2 is just a number, right? We could leave it in exact form like this, or put it in our calculator to get a decimal approximation. All right, so now we're going to use the one-to-one property of logarithms, right? We talked about that at the beginning for exponentials, But this is also true for logarithms. If you have the log of something equals the log of something else, you know that the things inside are equal to each other. Okay, so that's the key thing here. So we can set x squared equal to 2x plus 3. And now we've just got a quadratic, right? So we can bring these over to the same side. We can factor this, set each factor equal to 0, and we get that x equals 3 or x equals -1. All right, so here's an applied problem. How long will it take for 10% of a 1,000 gram sample of uranium-235 to decay? All right, so setting this up, we're going to have to think back to how we would set this up for an exponential. So here we go. Y is the amount that we have. It's continuously decaying, so it's going to be continuous decay. Our initial amount is 1,000. And then we have E to this times T. Okay. This is, let me explain. There is a table in your book that came right before this this problem that tells you that this is the rate. So sorry about that. You do not have to have this in your head. Okay, I would tell you what the rate was. It's the natural log of 1/2 divided by that big number. So you don't have to memorize that. So pretend you were given this information, okay? Because in the book it did give this information. All right, so now the question is, how are we going to solve for t? Okay. So the question is, when 10% is gone, what is the time, right? So if 10% is gone, that means we have 900 grams left. So we put that in for y, and we're going to solve for t. So we divide by 1,000 to get 0.9. Now we have this equation. It looks messy, but it's really similar to ones we just had. We can take the natural log of both sides, right? Natural log of 0.9, the natural log of this whole thing, natural log of e to some power is just going to be that power, right? This is a number. This is a number. So t is just going to be, we solve for t, right? Multiply by this 703,800,000 number, divide by natural log of 0.5, and it's a really long time, right? 106 million years for 10% of that to decay. All right, so this was sort of the end of this section. So let's think back. When we have different strategies that we used were to use the one-to-one property for exponentials, rewriting the base if we need to, so they have the same base and we could set the exponents equal to each other. We used the definition of logarithms, right? We used the clever trick to take the natural log of both sides. Those are pretty much the main ways that we solve logarithmic equations. Okay, so your homework will give you some different practice. Let me know what questions you have.